Good morning, students. Mr. Carver here. Today we're going to do section 8.3, and we're going to look at two additional tests to determine whether a series converges or diverges. Remember, in section 8.2, we started off with the first three tests, that is the telescoping series test, the nth term test for divergence, and then the geometric series test. So again, these are the next two. We're going to start off by talking about the integral test. And if I take a look at f of x and I am looking for the area underneath f of x, actually let me do that in black, f of x dx, and in this case f of x dx does approach 0. The function itself approaches the x-axis. The question then becomes, what happens when I just look at the area from 1 out to infinity? And as we know from the previous chapter, it depends on how quickly that curve gets to the x-axis. That will then determine whether the area underneath the curve is infinite, which it diverges or converges to a finite number. And I think I talked about in the previous video the fact that we can relate this then to the growth behavior of a series. And let's take a look at a series that goes from 1 to infinity, a sub n, and let's just assume that your f of x and your a sub n are essentially the same function. The difference being that f of x is a continuous function and a sub n is a discrete function where you just get integer values for your y's. And of course we know that the domain of any sequence is the set of positive integers. So I'm just getting those red dots as opposed to the smooth curve with f of x. If you think about the y values for each one of the numbers in that sequence as being the height of a rectangle with a width of 1, then I can think about the sum, or the sum of this series, as being the combined total of the areas of each one of these rectangles. I think it then also makes sense that if the area underneath the black curve is infinite, that is, it diverges from 1 to infinity, then the area contained within all of those rectangles from 1 to infinity would also be infinite. I think it also makes sense then that if the black curves approaches the x-axis quickly enough in order for the area to be finite, then the combined area of all of those rectangles will also be finite. Now, they won't be the same numeric value, but they will be both finite. Right? The fact that you've got these, that your two totals will be off by the sum of the areas of those like blue areas there, doesn't matter. If one is finite, the other is finite. If one is infinite, the other is infinite, and that essentially is what the integral test is all about. So let's take a look at the formal wording for the integral test. So the first portion says, if f of x is a positive, continuous, and decreasing function for x values greater than or equal to 1, and what we'll do is we'll let a sub n equal the same expression as f of x. Then the series from n equals 1 to infinity of a sub n and the area from 1 to infinity of f of x dx will either both converge or both diverge. So again, if the area is divergent, then the sum of the areas of the rectangles with width of 1 will also diverge. Likewise, as I said in the previous screen, if they both converge, or rather if the area converges, then the sum of the area of the rectangles will converge as well. All right, so let's take a look at an example. Let's say I've got, the infinite series from n equals 1 to infinity. Let's do n over n squared plus 1. Remember, the first thing that you want to do is take a look at the sequence and ask yourself, does the limit as n goes to infinity of n over n squared plus 1 equals 0? If this goes to anything other than 0, you know that the series will diverge by the nth term test. So let's check this out. If I plug in infinity for the n's here, I get infinity over infinity, which we know is indeterminate. I'll use L'Hopital's rule, which gives me 1 over 2n. Take the limit as n goes to infinity. That does give me 0, which means that the series potentially converges. We don't know yet. That's what the first half of Chapter 8 is all about, and that's what the integral test is going to help us determine in this case. So what you want to do is you want to look at your a sub n there and ask yourself, is it integratable? And if it is, we can use the integral test. Now, of course, it needs to be continuous from 1 to infinity. It also needs to be positive and decreasing. And as you can see, if all my n values are positive, I will get a positive expression. And in addition, the function or the dots in the sequence they are decreasing, right? They start at what, 1/2, and they go steadily downward toward 0. So I can use the integral test here. What I do is I just change them into x's and investigate what happens as I go from 1 to a, driving a to infinity. So in this case, we can use u substitution. U is x squared plus 1. Du is equal to 2x dx. This is nice. We're going to get practice at integration. I don't need the 2. Bring that over to the other side. This gives me the integral of 1 over u du going from 1 to a, which of course we know gives us the natural log of the absolute value of u, which is x squared plus 1, evaluated from 1 to a. I'm going to take then the limit as a goes to infinity of the natural log of a squared plus 1 minus the natural log of 2. If you recall, the natural log graph looks something like this. This goes all the way back to Chapter 7. As a goes to infinity, so does the natural log minus some finite value there. So this is, in fact, divergent, which means by the alternating series test, that is wrong. By the integral test, the sum from 1 to infinity of n over n squared plus 1 also diverges. And of course, I'm looking for all of this work. And I'm looking for the test that you're using. So by name, I'm looking for the integral test. And then, of course, all the supporting work. And lastly, I'm looking for your conclusion here. I'll be grading all of that. All right, let's take a look at another one. How about the sum from n equals 2 to infinity of the natural log of n all over n cubed? Again, the first thing we want to take a look at is a sub n and ask ourselves, does a sub n go to 0 as n goes huge? This is indeterminate, so we will use L'Hopital's rule. The top goes to 1 over n times 1. The bottom goes to 3n squared over 1. I copy dot flop. I get 1 over 3n cubed. Driving n to infinity makes it 0. It is bottom heavy, which means, again, the series has a chance at convergence. Now, assuming this went to, say, 8, then the series would diverge by the nth term test, but it ain't 8. It's 0, which means more investigation is required. It's sort of like having an indeterminate answer. If the sequence goes to 0, the series may or may not converge. That's what the first half of Chapter 8 is all about. Let's get rid of this. Of course, I want you to keep that L'Hopital's rule, all that supporting work for your sequence, because that's going to be part of what I'm grading. All right. Now, the next question becomes, which test do I use? One thing I notice here is that if I integrate from 2 to infinity, the natural log of x over x cubed dx, I could probably come up with an answer. I'm thinking we're going to use integration by parts. So my u is equal to the natural log of x, dv is equal to x to the negative 3 dx. That is dv, not du. All right, when I derive the natural log of x, my du is 1 over what I'm logging times the derivative of what I'm logging. My v then turns out to be x to the negative 2 over negative 2. So that's 1 over 2x squared. All right, let's put it together. This is going to give me negative natural log of x all over 2x squared minus a minus, that's plus the integral, of 1 over x cubed, and I can pull the half out front. That's x to the negative 3 dx. This gives me the negative natural log of x all over 2x squared. This is going to be equal to minus 1 over 6x squared, and I'm going to integrate this from 2 to a, taking, of course, the limit as a goes to hugeness. And I think I've multiplied this wrong. This is actually a 4, not a 6. All right, so let's go ahead and evaluate this. This is going to give me negative ln of a all over 2a squared minus 1 over 4a squared minus then, when I plug in 2, negative ln2 all over 8 minus 1/16. So let's take a look at what happens when I plug in infinity into a. I believe that this is infinity over infinity, which is indeterminate. Let's Lopatize that. That gives me negative 1 over a times 1. This gives me 4a, which gives me negative 1 over 4a squared, which goes to 0. So this whole thing, this first part here, actually goes to 0. Minus, I've got 1 over 4 times huge, which is also 0. 0 minus 0 is determinate. That does give me 0. Minus some finite number. So this will converge by the integral test. By the way, it doesn't matter really what this is, some finite number here, because remember, they don't converge to the same value. What we're finding here in green is actually the numeric value of the area beneath natural log of x over x cubed. I just am looking for the relationship between the behavior of the integral and the behavior of the infinite series, because they will be the same. So that means that my infinite series here from 2 to infinity of ln of n over n cubed will converge because the area converges underneath the corresponding function. All right. All right, now let's take a look at the p-series test. And this test is also closely related to the area underneath the curve. And if you look back in your notes, I did, for section 7.8, when we did improper integrals, I actually talked about, I worked 2 separate problems, and one was this, one going from 1 to infinity of 1 over x dx, and one going from 1 to infinity of 1 over x squared dx. One converged and the other diverged. So let me give you the wording then of this theorem, and I can show you how it works. So if P is a positive constant, then the infinite series from n equals 1 to infinity of 1 over n to the p will converge if p is greater than 1, and it will diverge if p is less than or equal to 1, greater than 0. It's kind of awkwardly written there. Let me clean this up a little bit. So if p falls between 0 and 1, inclusive of 1. And that's actually what you're seeing here if you look at the area underneath the curve. The area from 1 to infinity of 1 over x dx diverged. And if you look at the exponent there on your x, that's 1. And then if you go 1 over x squared, that will actually converge. And again, it's a function of how quickly the function itself, or the y values approach the x-axis. 1 over x takes a more leisurely approach. It doesn't get small enough quickly enough in order for the area to stop growing. Whereas 1 over x squared, the numbers get small very rapidly. Rapidly enough, in fact, in order for the area to be finite. So that's, again, what you're seeing here. Your p-value in the second one here is greater than 1, which means the area converges. P-value of 1 in the first one, on the left one there, will diverge. Same thing happens for infinite series. Now, I should mention that it is important that your series be in the form 1 to infinity of 1 over n to the p. Getting close to that form is not good enough. It actually has to be 1 over n to some power. Now, I will mention this. This 1 here doesn't actually necessarily need to be 1. It can be 2, 3, 4, 5, 6. Look, if the sum of the numbers is infinite, it doesn't matter where you pick up the sum at. The sum will always be infinitely large. Likewise, if your sum is finite, it doesn't matter if you knock off the first few n terms, it will still be finite. So these theorems still apply regardless of where the lower index begins at. Let's get rid of that. So let me give you a couple of examples here. Let's say I've got the first one here, the sum from n equals 1 to infinity of 1 over n times the square root of n. You want to put it into p-series form. So this is the same as the sum from n equals 1 to infinity of 1 over n. Same base, add the exponents, that's n to the 3/2. You've got a p-value that equals 3/2. That's greater than 1. So this infinite series will converge by the p-series test. I'm okay if you abbreviate the test, but again, I want you to show me how you're arriving at your conclusion. All right, let's take a look at what I was alluding to before. Let's say I've got the sum from n equals 1 to infinity. Let's make some room here. Of, let's do 1 over n squared plus 1. Now, I mentioned before that it has to be in this form. This is not in that form. So while you might want to use the p-series test on this, the plus 1 is problematic. It prohibits you from using the p-series, so you've got to use another test. In fact, I think what we'll use here is we'll use the integral test. So this is the same as 1 over 1 squared plus x squared dx, going from 1 to infinity. My a value is 1, my u is x, du is dx. I'm, of course, heading for the arctan function. That is 1 over 1 times the arctangent of x over 1, going from 1 then to a. The limit as a goes to infinity. And here we go. I got the arctan of a minus the arctan of 1. If you recall, the arctan of infinity is pi over 2. Arctan of 1 is pi over 4. This gives me pi over 4. So it converges by the integral test. Do not use the p-series test. It has to actually be in that form, as I said before. All right, guys, I think that's enough to get you through tonight. Thank you.